Okay, so I noticed that in this room there are at least 2 people who does not understand Korea. So I guess I will give my lecture in English, if you don't mind. Okay, so we have about an hour until we have lunch, so I guess you must be very hungry. So considering that, I prepared my lecture very easy. So the topic that I will discuss today is about the shock, which happens for compressible flow. But as I know, in Korea, there are not many experts working on the compressible flow yet. So moreover, so there is not many experts working on the shock problems. So today, the purpose of my lecture is to give really the beginning part about the shock problem. So after all, I hope that I have time to explain how we understand the shock from a mathematical point of view and how we formulate the shock problem, which is originally a physical problem, as a problem in PDE. So after all, at the end, you will see that the shock problem now finally becomes the free boundary problem, which contains nonlinear mixed type PDE. So I hope that I can tell you all this story in 1 hour. Okay. So what is shock and what is compressible flow? So first, well, roughly speaking, shock is some discontinuous transition which happens in gas dynamics. And why does it happen? So in order to say that, first I have to assume 2 things. So we consider shock for compressible flow only. Okay, so in the morning, Professor Choi gave the lecture about the incompressible flow. So what is the main difference between those 2? So basically, the main difference between the incompressible flow and compressible flow is on the density. So if the density of a flow is remain constant, then we have incompressible flow. But if density is a function, not a constant, then we have to study compressible flow. And for compressible flow, if there is no viscosity, then we get a shock. So here, what is the role of the viscosity? So mathematically speaking, viscosity gives you smoothing effect of the solution for the PDE. So if you remove the effect of a viscosity, then you can consider a solution for PDE which has discontinuous transition. So from now on, I will assume my flow is compressible, which means that the density of the flow now becomes unknown of your PDE. So we consider compressible.
학생들은 잘 봐요.
And then, so no viscosity, which means our flow is inviscid. Okay. All right. Then the equation which describes the motion for compressible inviscid flow becomes Euler system. So you look at the Navier-Stokes equation. There you put the compressibility and you remove the viscosity, then you get your Euler system. And then, so well, fundamentally the Euler system basically is a mathematical formulation which describes 3 conservation laws. So what is the conservation law first? It's very easy to understand, all right? Okay, so in the space, so I will just assume Rn space where the dimension can be any dimension you want. So we fix a domain U as a subset of Rn. I will also assume that the boundary of U it is C1, so that I can imagine the normal vector field on the boundary of this domain U. Also, U is connected and bounded, just to simplify the argument. So you just imagine some domain U in the space, right? And then we can also, since the boundary of U is C1, we can consider outward unit normal vector field surrounding the boundary. So I will just say N is a unit normal vector on the boundary. Okay, then, well, whatever the here Q is, I will assume that Q is the density of some physical quantity. So it can be this really physical density of a flow. It can be anything, well, in the area you study, okay? All right, then, here the quantity F will be the flux. So what is the flux? So given some particle, you are basically tracing how this density is moving around in your domain. So this will be flux. And normally in physics, the flux depends on the density Q. So normally f becomes the function of a q. So the density here, the scalar function, so this is defined in the, so here I have a spatial variable and time variable. So here q is a function defined on the domain u cross the time variable r plus, and then this maps a number r in the scalar density. Later actually we will replace this by as a vector in Euler system. For the flux, this depends on q, so this is a function from here r to Rn. So this is a vector field because in the space you have many directions that you can go for the flux. So this is the flux. So what is the conservation law? It's very simple. So now you are measuring, so here if Q is the density, you know that the total mass of a Q in the domain is simply the spatial integral of the density Q on the space U. Okay? And then here, Q is the function depending on the spatial variable x and t, where x is a spatial variable, so this is Rn variable. So now this integral becomes the function of a t. So you can consider the derivative of this with respect to time. So if we take the derivative with respect to time t here, now this was, what does this mean? So you look at the total mass, and then you take the time derivative. So this measures the change of the total mass in the domain U, right, with respect to time. So physically, if there is no like the artificial the input or output, so the time derivative of a total mass depends on the total flux coming through the boundary with you, right? So you simply look at what happens on the boundary, then you will automatically know what happens to total mass in the domain U. So since this becomes the total the surface integral of the flux in the normal direction, because if there is a tangential direction, there is no contribution in the change of total mass. So you look at this. This is a surface integral on the boundary of U. But if you have outgoing flux, that gives you the negative contribution to the total mass. So you have negative sign in front of this, right? Okay. Now from now it's really calculus. So here you see you look at this right hand side, and you do know very well-known divergence theorem. So if your vector field F has the regularity good enough, you can simply apply the divergence theorem. So you get this becomes integral the omega. So basically I want to make the integral on both sides comparable, and this becomes minus divergence of the vector field FQ in the domain X. Okay, so another thing. So for this time derivative, you can simply put this in the integral, right? Just formally speaking. Then, you see, okay, so I already changed this to omega is the symbol I normally use. So here U, right? Okay, now another thing that you have to remember, so this is a conservation law, right? So what happens to the inside basically depends on what happens on the boundary. And then here U, well, so this is integral equation for Q, but in fact here U can be arbitrary. The conservation law must hold anywhere. So by just simply removing this integral U, you end up with this differential equation, the famous conservation law equation. So here divergence is with respect to X, right? So this is your conservation law. So whatever is conserved. So this is the conservation laws. So as you can see, the equation for conservation law is nonlinear, right? So that's why we can construct shock solution for this guy. Okay. So far I only talk about the general conservation law. So now using that, now we can formulate the Euler system. Okay, so what is the Euler system? So like I said earlier, Euler system describes the flow motion for compressible inviscid flow. And what is the physical law to describe the motion of this compressible flow? Well, if you take the general physics, there are three conservation laws, right? So there is conservation of mass, there is conservation of momentum, and there is conservation of energy. So basically, Euler system is collection of all these equations describing these three conservation laws. So we can easily write down the conservation laws here, the Euler system. So from now on, I go back to Euler system. So for that, now I need to introduce the vector which describes the physical quantity of my flow. So here I'm going to use rho as a density of flow. And there is a velocity, of course, u here, and then this is a vector function, right? So this is velocity. And there is P, which is pressure. So if I consider n-dimensional flow, I have n plus 2 unknowns for my system. So therefore, I need n plus 2 PDE to solve. Okay, then, for the Euler system, so what is the conservation of mass? So here, that if the rho is the density, you can simply apply this conservation law equation for each conservation law. So for Euler system, so for conservation of mass, so now you can imagine what it's going to be, right? So here, mass is related to density. So if we write down the conservation of mass equation, so this is going to be rho t plus divergence of the flux. And what is the flux? So basically, particle is moving through the boundary depending on the velocity. So flux simply becomes rho times velocity vector field over u, right? So this is conservation of mass equation. Momentum, same. So what is the momentum? So momentum is basically the product of the mass times the speed, right? Or mass times velocity. So for momentum, you see you have n different direction for the velocity vector field, right? So if you say here u, in fact, this u has n component. So you can consider conservation of momentum in n different direction. So here, for example, in j direction, the momentum is going to be rho uj. So here, this j is j's component of velocity vector field. And then here, this time t. So this becomes the density for the momentum. And then the flux. So here, there is a little bit different, the more physics. So for the flux, of course, you will imagine that the corresponding flux is going to be rho uj times u, like the mass equation. But for the Euler system, there's a microscopic interaction. So regarding that, so I included some part of the book by the famous Courant and Friedrich, if you look at this guidebook. So there is more physical background of this equation. So considering, okay, so the microscopic interaction, so you have here P times, so here P is the pressure, and here EJ. So EJ is the unit vector in J's direction. So this is the momentum equation. And then this must hold for J equals to 1 to n. Right? Okay. So this, well, now you have already n plus 1 equations, right? Moreover, actually, sometimes we can even write this in a simpler way as the following. So this I can write as rho u. So now this becomes system T plus divergence of x. So now, so in order to just generalize this as a vector, I'm going to use this tensor product. And then here you will imagine that this becomes P times In, where In is the n by n identity matrix. So this becomes the equation for the momentum. Okay, now for the energy. So I'm going to just write down. So for the energy density, so, well, you have basically kinetic energy plus additional energy, which we call internal energy. So here the energy, rho times E. So I will tell you what E is in a minute. So this is energy conservation. So this E is energy density, of course, plus divergence X. And then here, rho times E plus. So now I'm talking about the flux here. Same thing. So you need to consider this microscopic effect. Okay, times U equals to 0. So here, what is E? So E is the summation of kinetic energy. So kinetic energy, well, you already have a rho here, so 1/2. speed square plus here small e. Here small e is internal energy. So normally this depends on P and rho. So this relation will close the system, right? So now totally you have n plus 2 equation with n plus 2 unknown. So now you have a complete system. And also from now on, we'll look at the polytropic gas. So I will specify now our model. So if we consider polytropic gas. So in the study of Euler system, many people study this one because air, as we know, is also one of ideal polytropic gas. So ignoring all this physical meaning of that, for ideal polytropic gas, this internal energy is given by the following relation. So E is going to be P over gamma minus 1 over rho, where here gamma is a constant bigger than equal to 1 normally. So for example, air has this constant gamma is about 1.4. Okay. So now you will notice the air is also in the category of this flow, which is described by Euler system here. Okay, so this is unsteady Euler system. Now, of course, from now on, we will look at this system and talk about the shock solution for this Euler system. Okay, so as you know, this is already complicated enough, and this is a nonlinear system. All right. So to simplify our argument, now I will even simplify this model from now on. So you see our solution depends on time t and x. So here there are many different studies about the shock solution for Euler system. And one of the study is the study about long time asymptotic solution. So what is the long time asymptotic solution? So let's look at the following case. So suppose that if there exists, or suppose that if, let's say here V, which is a vector, is rho, u, and p, which is the function of x and t. So if this solves the Euler system here, so let me label this whole system as just capital E. So if our system solves the unsteady Euler system E, right, for all x and t. So here I didn't specify the domain, but let's say just for any x and t, right? And if there exists a vector field V tilde, now this is given by the following. So now I have tilde, and this is a function of x, such that here this function v converges to v tilde, okay, as time goes to infinity. I also need to tell you what is the norm of the convergence. Well, for simplicity, let's say C1 in x and t, okay? Then what can you say? Then, well, as you see here, v tilde is independent of t, but now this converges to v tilde. So therefore, well, the derivative of v tilde will satisfy this equation, of course. Moreover, v tilde is independent of time variable. So after all, the equation for v tilde becomes the following. So basically, you look at this Euler system, remove all the time derivative term. So therefore, v tilde now becomes the solution of, so then v tilde solves the following. Here, divergence of rho u, so here I have x equals to 0. So this is a zero vector, and there is energy. Okay, so for now, applying the definition of E plus applying the definition of small e, internal energy for polytropic gas, now I have here is rho, u, and I'm giving a new symbol B, which is the following. So here B is 1/2 u squared plus gamma p over gamma minus 1 rho. And here gamma is assumed to be bigger than 1. Now why do I give this symbol B? Actually B had a special name. So B is called Bernoulli's invariant. So from now on, so I will study this one. So what am I doing here? So now I take a solution of unsteady Euler system and I look at it a long time asymptotic limit. So basically I'm studying what happened to the solution for unsteady Euler system. So you have this where compressible viscous flow, you just keep observing it and you study what happens at the end, right? So this will convert to some steady state. So I'm studying this steady state. And then by understanding this steady state, I hope that I can understand in some aspect about the behavior of solution for unsteady Euler system. So that's my goal. So from now on, so this will be the equation we study. So let's call this is E1 and E2 and E3. So I will talk about the shock solution for this system. Okay. So now, so what is a shock? So now I need to tell you what shock is. So in order to understand what the shock is, so we need to do some computation. Well, we are going to just do some integration by parts. And this is a part where I got shocked when I learned about shock problem for the first time, which is 10 years ago. Okay, so intuitively, now you will imagine the shock is a solution for PDE, but the solution has discontinuity, right? Now you are looking at the solution of a PDE with a discontinuity, which means that you have to somehow define some sense of the solution, the shock solution for Euler system. So here, so imagine a nozzle. So this can be any shape, but for simplicity, I will look at the flat nozzle for today. So we don't know what the shock is yet, but let's say there is a shock. So basically the shock is it could be the curve, right? If you look at R2, it can be like the height of surface, if you look at the n-dimensional space for any n, right? The shock is basically curve or surface where you have somehow dramatic change of your flow. So there is a somehow smooth flow before the shock, but after the shock, somehow it changes character discontinuously. Somehow the speed will change after all. So this is my solution. So from there, so I'm going to call omega minus is the domain before the shock, and omega plus is the domain behind the shock. Well, before is not a good word because this is now steady state. Okay. Now I will assume the following. So suppose that here rho, u, and p. Now I'm not assuming this is the solution of that yet. Let's just say there are some functions which is in the following space. The C1 of omega plus minus, which means that away from the shock it's C1, right? Up to the shock S here. Also, it's L2 across the domain. So what do I mean by that? In the whole domain, I don't expect my solution to be regular. But in each of subdomain, away from the shock, up to the shock, right? If you split this two, right? There's omega minus time and S, omega plus and S. In each subdomain, you expect your solution to be C1. So therefore, you expect this to be the really classical solution of that system. Okay? All right, for such class of solutions, well, not functions, right? Now we do the integration by parts. So here we integrate an omega minus and also omega plus. So I integrate separately of the following. Now I'm looking at the conservation of a mass. So your divergence x of rho and u. Okay? But I don't know whether this is 0 or not yet because I'm not assuming anything about this function yet, right? Now you multiply some test function eta here. So what is eta? Eta is just some smooth function with a compact support in omega. Okay, eta can be at some test function, and I integrate. Okay, then I start integration by parts in each omega minus and omega plus, right? So let's look at the integration by parts in omega minus. So if the support of eta is somewhere around here, right? Then, okay, first, on the boundary of omega minus, by the integration by part, this is going to be rho times u dot n minus, well now I need some word here. So what is n minus? So n minus is basically outward unit normal vector on the boundary of this omega minus. But as you can see, eta already vanished over here. So the only place where eta survives when you do the integration by parts is over there. So n minus is going to be unit normal on the shock, right, toward omega plus, because this is outward from omega minus. So this is n minus. Okay? So actually this integral only survives on the shock s. So I'm only looking at this. Just to avoid any confusion, here u is evaluated from this side. So just to say that, let me give you this index minus, just to tell you that this is a value taken from here. All right, so this is the surface integral. So let's say dA minus, dA, and then minus, integral omega minus, and then rho u, that with the gradient of eta. Right? So this is just integration by parts in omega minus side. And you do the same for omega plus, right? So this is a plus integral s, here rho u plus dot n plus. Now where is n plus? So n plus is outward unit number for omega plus. So this is unit number on s toward n plus. So now you start seeing the relation between n minus and n plus. Actually, this will give us some special condition later. Okay, so here, plus here, dA minus integral omega plus rho u dot d eta dx. Okay, just integration by parts. Nothing new, nothing fancy here. So let's combine them. So we combine this in the following way. First, you notice that from this picture, n minus and n plus basically has this relation.
아무노래 에타가 빠진 거 아니에요?
네, 맞습니다. 에타. Okay. So now we can combine this integral into one as follows. So integral on s, right? And then rho. So let's say rho plus, well, here I have minus first. Minus, right? Dot n. Well, let me just say the following. Dot n, right? So here n is n minus times eta dA. For this integral, you can just simply combine into one, right? Because we have the assumption that rho and u in L2. So this is integral over domain omega rho u dot d eta dx. Okay. So for this class of functions, this integral is equal to that. So from there, what can you say? So we can say the following. If rho and u satisfy the following, integral rho u, well, let me use now mathematical terminology. I want to say this is 0 for any test function eta. Well, in mathematical point of view, this is a weak solution for which equation? For this equation. So rho u is, okay, if rho u, okay, let's say satisfy, first, weak solution of this first equation, E1, right, in omega, to rho u satisfy this relation. Now, let me use a symbol just to simplify the argument. So, I'm going to use this difference of the quantity as a bracket. So, if I say rho u, that here n is the unit normal vector on this surface S, right? If I say bracket, that means that I take the difference of this from both sides. They have a jump, right? We expect they have jump on S equals to 0. So, which means that if this guy is 0, this guy is 0, right? Then, what happened? Rho and u satisfy this, and here eta is any smooth test function, which means that, well, they satisfy this equation pointwisely, right? Then, rho u satisfy divergence of rho u equals to 0 pointwisely in omega plus and minus. So we don't care what happened across the shock yet, but somehow this is the relation, right? So from this computation, now we can generalize the notion of a shock solution for all the system. And now here, important thing is this. So this tells you how to identify the location of a shock. Okay? So now we give a definition. Well, here, but I don't want to say shock solution, so I will say the following. The rho, u, and p is a solution of the steady Euler system, E1 to E3, with a discontinuity. I didn't say the word shock yet, and for some reason, the discontinuity S. If first they are in the class of piecewise C1, omega plus minus, union S, intersection L2 omega. If they is first a weak solution of this Euler system, 2, and they satisfy the important so-called Rankine-Hugoniot condition. So I will write down what they are over there. Condition on S. So what is the Rankine-Hugoniot condition? The Rankine-Hugoniot condition is the following here. So from now on, let me use RH condition. So this is the terminology I normally use. So what is the Rankine-Hugoniot condition? We already have one Rankine-Hugoniot condition, which is this. So first, the jump of momentum in the normal direction on this discontinuity S must be balanced. So what this means is physically somehow something is discontinuously changing. But even so physically, in order for this to make sense in physical sense, they still somehow satisfy some balance law on both sides of the shock. So here for momentum, same, right? So now you just go through the integration by parts for this equation. Then you will get again the vector equation, which is the following. So rho u dot n becomes U plus Pn S equals to 0. Also, you have the equation for the energy. Okay. So this is the first set of a Rankine-Hugoniot condition. Okay. So now I can tell you how do we study the shock problem in physical sense and mathematical sense. In order to study the shock solution for Euler system, basically what you have to do is to find out the weak solution of this system. Plus, we have to find the location of this discontinuity S, so that our solution satisfies the Euler system in distribution sense plus this equation. Okay. So here S, you see, S is a kind of a boundary in our domain. But S is not fixed yet. We have to find it in the process of a solving problem. So mathematically this becomes free boundary. So now we have a free boundary problem for shock. So shock problem. But I didn't tell you, well, earlier if you remember what I said, the shock problem after all will become the free boundary problem with a nonlinear mixed type PDE. So where is nonlinear mixed type PDE? So now I will tell you this. Okay? But before we do that, well, you may be confused. I'm talking about shock, but I only said discontinuity. So why is that? The reason is the following. If you look more closely for this Rankine-Hugoniot condition, this will give you two different types of discontinuity. One is the shock, one is the vortex sheet. Okay, so I will actually tell you how we classify those. The problem is over here, which is a vector equation. Now, let's say here tau is the tangential vector field for the discontinuity S. So therefore, tau of course is perpendicular to our normal vector. So if you take the dot product of this equation with the tau, what do we get? So this gives you only this equation, right? So you notice that this tau will disappear. Moreover, now if you look at the inside of bracket, there is this quantity. But what do we know? From RH1, this value is the same on both sides. So you can rewrite this into the following. So we can consider two cases. Now here, rho is the density. If rho becomes 0, it becomes a vacuum. Then things get really bad. So I will assume that rho is positive. Okay, I'm only looking at non-vacuum state. Then we have two cases. Case 1. Well, I'm talking about discontinuity, right? So either this guy is 0 or this guy is 0. It's impossible that both guys to be 0 to have discontinuity. So you can easily notice that from this relation. So either this guy is 0 or this guy is 0. Or I can say either this guy is 0 or this guy is non-zero. So I will assume that, well, if this normal component is not 0 on the shock, I already said the answer, on the discontinuity S, then what happens? Then this guy must be 0, right? So we have tangential component to be 0, right, on this discontinuity. And then I have two other conditions here. And here. Okay. Now again, for this guy, but from the first condition, this is the same on both sides. So this you can even rewrite as the balance of a Bernoulli invariant on both sides. So something is preserved. Well, I keep saying shock. Okay. So this is the case where you have a shock. So this is a shock. Okay, what is the other case? To the other case. So the other case is when the normal velocity vanishes on the shock. Then what happens? Well, then the only thing you can say is from here. There's nothing you can say from here and here because they already hold, right? So from the second condition, you only have the balance of pressure. Okay. Actually, I missed something. Okay, for this condition, I also have other thing. So second case gives you vortex sheet. Or I normally use the terminology contact discontinuity, VRC. Or vortex sheet. So let me give you a picture to give you the idea for the difference between those two. For the case one, so suppose that there is a shock there. Then if there is a incoming flow toward the shock, then you see there is a balance in the tangential components of the velocity. So behind the shock, you may expect your flow will become something like this. They will turn the direction, but they still preserve the same tangential projection on the shock. So this is a shock. But there is a jump of a pressure and everything. Now for the vortex sheet, so normal velocity vanishes. So around this vortex sheet or contact discontinuity, the velocity is like this. Something like this, right? There is a jump of a tangential component of velocity. Then what's going to happen? So you can imagine that there's going to be the vorticity blow up. So that's why you get the vortex sheet or contact discontinuity. Now in this field, for compressible flow, study of both cases is a big deal. So far, the understanding about contact discontinuity is less done. Now the understanding about the shock, well, now we are making some develops. So that's what I will tell you today. So if you are interested in this field, you can consider working on those cases. Or physically, there are even cases where at one point a shock is coming. So this is a shock. And then it got reflected by some obstacle. Then they split into two shocks. Okay, so those are all shocks. But if you look at the reference that I gave you about Courant and Friedrich, there is a very well-known statement that says that it is impossible for three shocks to meet at one point. Then how do we, what happens? Then there will be contact discontinuity happens between two shocks. So this pattern is called Mach reflection. So sometimes, in order to study compressible flow, one has to look at the case where both shocks and contact discontinuity appears. But so far, nobody can do that. So people, what people usually do is either they study shock, either they study contact discontinuity, and hoping to combine those results at some point in the future. Okay? All right. So now I gave you every ingredient for the formulation of shock problem. So now, I didn't give you any examples. Is it possible to construct a shock mathematically? Yes, so it is very possible. So as a simple example today, I will give you an example of a one-dimensional shock. And for two-dimensional shock, if you look at the reference that I gave you in this guidebook, you will see the section for oblique shock. So this is the example of two-dimensional shock. So if you are interested, so you may read it. Okay, so here I will keep this. So example of 1D shock. So what is 1D shock? All right. So we still consider this flat duct in Rn. It can be in Rn. Now we expect to construct the shock in the following way. So there will be a shock which is perpendicular to the boundary of this nozzle, and this is called the normal shock. Okay, and on both sides of the shock. So before the shock, there is a horizontal flow coming, right? So if you look at the velocity here, so it will have the following representations: U minus times E1. Okay, and after the shock, there will be jump of velocity, and then the velocity representation is going to be U plus E1. So here, U minus is different from U plus. So I will construct this solution for all the system, okay, so that they satisfy this Rankine-Newtonian condition too. Now, I can work with this full system, but now I'm already running out of time, so I will assume some conditions for simplicity. Okay, so simplification. Of all the system. So I will just give you a word and then you can check later. All right, so first, if you look at the second equation, E2, so this is a vector equation, right? So I can take the dot product of this with E2. Okay? And then you subtract E3 from here. And you get 0, of course, on the other hand, right? If you do that, you will see that the following quantity, well, let me write down the equation. So U dot and gradient of ln of P over rho to the gamma. So this quantity becomes 0. So physically speaking, this means that the entropy, so what is entropy here? So you know, you are familiar with the terminology, right? So this guy is the entropy for ideal polytropic gas. So this entropy satisfies this transport equation. More precisely speaking, in smooth flow, so actually this is based on the assumption that our solution is C1 for the moment, so that I can do all the chain, product rule and everything. This means that the entropy is preserved along the particle in smooth flow. Okay? Also, if you look at E3, so let's look at E3. E3 I can rewrite as follows. So this is divergence of rho U times B, just calculus. So U dot B, gradient of B equals 0. But from the conservation of mass, so this is already 0. So what this equation gives you is conservation of a Bernoulli invariant along the particle. Along the trace of a particle, I mean. So we have these two conditions. So from there, I will simplify the system. Okay, so these two equations will hold if entropy and Bernoulli invariant are assumed to be constants. This is just for simplification. So I will assume that here P over rho to the gamma is a constant, say kappa 0. And here B, okay, so B, what is B? So B was 1/2. Now you see that we are looking at 1D flow. The speed just becomes U squared, where U is the speed of flow, plus, now your gamma P rho gamma minus 1 rho. So by this relation, so this becomes gamma kappa 0, gamma minus 1, rho to the gamma minus 1. So we will assume this quantity to be a constant B0. And if you look up some papers about this Euler system, quite often this equation is called Bernoulli's law. Okay, so I will assume those two, okay? Then we can really simplify our system. So let's see. For 1D, right, I'm only assuming that my solution is a one-dimensional solution. Then this PD becomes ODE. So here E1 just becomes rho times U x derivative equals to 0, right? And then here E2 will just give you P equals to kappa 0 rho to the gamma. And then E3. Now here is the point. Well, actually you can solve this equation for rho, right? So by normalization, we can assume that this is 1 for simplicity. So you can always do that by rescaling the variable. Then you see that E3 gives you the algebraic relation between the density and speed, which is the following. So rho equals to B0 minus 1/2 U squared and 1 over gamma minus 1. So what does that mean? Well, we can even plug this back, right? To here. So, okay, I hope that I can finish the whole story in 5 minutes. So then, this E1 now finally becomes B0 minus 1/2 U squared, 1 over gamma minus 1 U, okay? X derivative equals to 0. So I reduced my system basically into an equation, just one OD for speed U, and the other two are just algebraic equations. So by solving this equation, if I find out my speed, then I find out my pressure and density, okay? And this is called isentropic model. In sense that I assume my entropy to be globally constant. But physically, if there is a shock, it's not true. So one really has to worry about the jump of entropy. Then the story gets complicated. But today I will just assume this isentropic condition just to give you an idea about the shock. What about the Rankine-Hugoniot condition? Okay. So here, now I already assumed the isentropic condition and Bernoulli's law. Well, here you see that Bernoulli invariant anyway is preserved. And I simply assume that my Bernoulli invariant preserved by a constant. So this already holds. For isentropic condition, I cannot involve this because this implies a jump of entropy across the shock. So I will just forget about this. So the only condition I have, well, in the 1D, so in 1D you see the normal direction is, well, just this becomes the speed itself. So I have rho plus U plus, which is the, well, the value after the shock, must be equal to rho minus U minus before the shock, so on the shock S. But I don't know where the shock is yet. Okay? But this is my condition. But moreover, you see, I already represent my rho by this. So this actually implies the following. So let me call this quantity inside of OD by G of U. Then this Rankine-Hugoniot condition implies G of U plus equals to G of U minus on the shock S. Okay, but you also remember we have one more condition to be held at the shock. What is this? Tangential component must be balanced. But I'm looking at the 1D flow, so this already hurts, so I don't worry about that. So I only need to look at this and this, okay? Let's see. If you look at the equation, this means that in smooth flow, this must be a constant. Okay? So here, from the equation, so let me call this is E1 now. E1 implies that G of U itself must be a constant, okay, along the shock. I'm sorry, in smooth flow. Actually, this is the same as G prime of U times, well, you hear X, where G prime Ux equals 0. So I'm looking at this. So anyway, this quantity inside must be a constant, M0, which I call total momentum. Okay, but also, this M0, well, principle, this can be different on both sides of a shock. But you have a balance law. From the Rankine-Hugoniot condition, this quantity preserved across the shock. So in fact, this M0 is a global constant, even across the shock. So you already have this relation to hold to construct the shock solution. Okay? So now using this, I can easily construct the solution. Now, more calculus. Let's graph the function G of U equals to M0. Let's graph this. Well, G of U, I only graph G of U. Okay, you just check, okay? So I will tell you the story. If you differentiate G, so you can check the following. If this speed U is less than some quantity, which is the following. So this one can easily compute, right? And this is positive. And let me call this U star. Okay, so at U equals to U star, this is 0. If U is bigger than U star, this is negative. The calculus. So if you graph G of U, and then from this relation you know that U cannot exceed 2b0 square root. Okay, so there is a U star here. So roughly speaking, the graph look like this. Okay. Now one thing you notice, if U is not equal to U star, G prime never be 0. So by looking at this equation, so if G prime is not 0, Ux derivative is 0. So you look at the constant solution. If U is not U star, okay? So now what I'm gonna do is the following. So here, I fix one point. And I call this U minus. Okay? And at this particular U minus, you see this guy is negative, which is not 0. So this simply becomes the constant solution of my ODE. So I give my U minus. Then I'm curious, if I fix my incoming speed by U minus, so what's gonna be the corresponding state U plus behind the shock? How can I find it? Well, I have this relation, right? If GU minus given, then the only possibility to choose U plus is to look at intersection for horizontal line, right? At GU minus. And you see that there are only one solution, which is different from U minus. So I look at U plus. So for such a U minus and U plus, I can say, okay, so if you start with this incoming flow, then you have a shock S, and you will jump down to this U plus state. So this is how you construct this solution. Okay? Now, one may ask, is it possible to go this direction? Mathematically, it's a correct solution, right? It does not violate any condition there, but it violates physical condition. So, important condition that you have to remember when you study shock is that across the shock, velocity always must jump down. You can consider this way. So you are driving on the highway, right? And then there is no car around you. And then you can speed up, right? You are looking at a fast flow. And then you see the red light. And you have to slow down immediately. Then the cars following behind you will slow down. Then somehow the distance between the cars gets smaller and smaller. And then you will stuck with all the cars. You have a traffic jam and so on. So that's how the shock generated, physically speaking. But you're going slow. But there is no reason why you speed up and you will stuck with the cars, right? So that is the entropy condition, right? So in order to construct the solution, shock solution, which does not, well, which is admissible physically, you also have to always remember the entropy condition. More precise version of entropy condition is that the entropy, earlier I told you that in the polytropic gas, basically this guy corresponds to the entropy. So this quantity must increase across the shock, right? But actually for isentropic flow, this does not jump, but something else is jump. So physically speaking, well, if this guy increase, well, if I don't assume that any isentropic condition, this is equivalent to the decrease of the velocity speed across the shock, or this corresponds to increase of the pressure or increase of the density across the shock. Okay? So this is how we construct the 1D shock solution. So now I'm already out of time, so I will tell you the story about open problems now. So for 1D, basically you do the OD analysis and you can easily construct a solution. Okay, so this is a flat duct, the easiest case. Well, another case is you can look at the divergent nozzle expanding the radial direction. then your ODE will slightly change. Then you will have some R variable here, but still ODE analysis. But what if your domain is curved? Okay, you have a fast flow, but then you somehow have high pressure there. Then somehow a shock must happen. Okay. Then, how do we construct such solution? Open problem. Because here, you see, if you look at the trace of every particle, they are moving in a different track. Which means that velocity, every physical quantity is changing in a multidimensional way. So you really have to solve PDE. For such solution, it's open problem. Also, well, 1D is easy, but if you go to 2-dimensional or 3-dimensional, the problem gets more complicated. Well, here, I only assume 1D flow, but if we go to multi-D flow, well, there are many factors to be considered, right? You have to worry about the vorticity, but in the multi-dimensional case, we can still we cannot still consider the shock solution with the vorticity in 3D case. In 2D case, we can do that. There are already tools developed. In 3D, it's open problem. So maybe for you, it will be actually good if you can make some contribution for shock solution in 3D with the full system. And moreover, there are many other open problems. So you can look at the reference that I gave you. Let me tell you one thing for 1 minute. So where does this, well, I still didn't tell you the mixed type PDE. Where does it come from? In this graph, I have this critical number U star. So this is called sonic speed. Physically speaking, if speed is faster than U star, this is called a supersonic. So you can imagine like the fire in the aircraft, like who can fly like 2 Mach, 3 Mach. This is really moving the Mach speed and the supersonic state, right? But mathematically, if you formulate the supersonic flow in the equation, this becomes hyperbolic. If the speed is less than U star, physically this is a subsonic state. So physically slow state. And if you formulate the equation, this becomes elliptic. Of course, at the moment, I'm only talking about steady state. If you go to unsteady state, the story gets a lot more complicated. So if you look at this flow, here, this is hyperbolic. And here, this is elliptic. Physically, supersonic, subsonic. So physically, you have a shock where the flow state changed from supersonic to subsonic state. So this is called transonic shock. And then here, well, so this is a 1D case, but if you want to study the multi-D case of this problem, one has to solve free boundary problem so that one side becomes hyperbolic, the other side becomes elliptic. What is the problem? When you solve the problem, you don't know this location where this transition happens. Then somehow you don't have enough control to get all, well, Professor Lee Ewan gave the lectures about this shadow estimate for elliptic PDE, but for that, in order to do all this kind of estimate, you need to know the type of PDE. Without that, you cannot do anything. But if you formulate this problem as PDE, well, there are many ways, but then you will see that the coefficient of equation depends on the solution itself. But you don't know the solution. Therefore, you don't know the information about coefficient. Then somehow you need to start building up some information, a priori information about the flow. And then that's when you get into all this PDE theory, hyperbolic PDE theory, elliptic PDE theory. You need to know how to estimate and to get the regularity and to get the solution at the end. So there are a lot of things to do. So for more information, so you can refer to the references that I gave you, and also so here in the material that I gave you, it's a part of the book Kurang Friedrich. But if you're interested, you can look at the book. That book is full of the open problems about this shock problem. Okay, so that I think that should be the end of my lecture, and thank you for your attention.